Hello, Zentnerds. How is everybody today? After working all summer of 1971 in the high Sierras of California, I started geology in 1972 at UC Santa Barbara. The following fall, I traveled northward to hang out with my friend Mike Macy, who was the backcountry ranger 11 miles up the Hoh River Valley in Olympic National Park. It was there and then that I first climbed Mount Olympus, shown here in the distance, and fell in love with the Pacific Northwest. I've often returned, but nowadays I enjoy the heat and sun in Tucson, Arizona. So here's my token shot of Silesia. Now, in today's slideshow, I want to answer a few questions posed by Zentnerds during the A to Z, and also to try to fill a few holes in the presentations. Some of the slides we're going to look at are pretty dense, so please just stop the video and study the slide in greater detail if you feel the need. We started down the path of collisions followed by big fault slices, but I want to emphasize that it's not necessary to have a collision to have big faults. Here's a great example from Indonesia where the Semangko, or Baresian Mountain Fault as it's sometimes called, slices the Sumatran arc without a collision, as originally pointed out by a geologist named Fitch way back in 1972 or so. There, although movement of the Indian plate is northward, subduction is orthogonal to the arc, as shown by the various arc volcanoes, which are shown as stars here. So note that the distance between the Java Trench and the active arc volcanoes is the same all along Sumatra and Java. So the subduction of the Indian plate is actually to the northeast, although the Indian plate is moving northward. Here's a terminology diagram for you showing just before a collision of a continent and an arc terrain, not to scale. But you can see on the continent is a passive margin, an Atlantic type margin, and as it enters the trench it has to go up and over the outer swell to the trench, which forms when the plate bends as it goes into the trench. Then next to it you have an accretionary prism, which comprises material that was stripped off of the lower plate and attached to the upper plate with the arc. Now here's a bit of what a continental margin might look like. This is an Atlantic type continental margin, much vertically exaggerated, but you can see the continental shelf, a slope, and then a continental rise out into the abyssal plain. This is typical of Atlantic type margins, non-active margins, as you will. Here's a cross section showing a typical Atlantic type margin with its rifted outer portion. You have stretched cratonic lithosphere there, and as it goes eastward, the cratonic crust is not stretched at all. And as the plate moves away from the rift or the spreading center, it subsides due to the cooling of the oceanic plate and also the load of sediment put on top of it, which typically comprises a basal clastic succession, typically finding upwards from sandstones to shales. And then if you're in tropical climates, you get a nice carbonate platform on top of that. And on the carbonate platform, of course, you have a outer reef which passes into deeper water. A bunch of debris tends to fall off it and stuff like that. So you might look for this kind of stuff in a collisional setting. Now, like I showed you, as the lower plate moves towards the trench, it has to pass up and over the outer swell. And at this time, whether it's typically continental, it erodes. The oceanic plate probably stays below the water. And off of Japan, on the east side of Japan, I think as I recall, there's a bunch of weird little basaltic volcanoes that come up along fractures in the outer swell. Anyways, continent's a little bit different deal. Continents, you tend to get a nice forebulge unconformity because the outer swell gets eroded, and then as it heads towards the trench, You might get a little bit of carbonate if you're in the tropics built up on top of it from organic organisms, and that's rapidly buried by hemipelagic marls or by mud. Basically, you want to think of mud, fine-grained stuff that's just settling out because there's no way that much is being eroded from the outer swell, and then that's buried by what are called turbidites, or flysch, which is interbedded shales and sandstones, or mudstones and sandstones. And they tend to be deposited longitudinally in the trench. In other words, they are transported along the trench. So here's what one of these things looks like. Here's the Rocknest Formation in Watmay Origin in northern Canada, overlain by the Recluse Group. And typical carbonate platform, easy to see. And above the basal, or above the lower part of the mudstones and hemipelagic stuff are turbidites. Great length in bed forms. You can see this is probably about maybe half a kilometer or so in across from left to right. So you got quite a distance of individual beds that you can follow. Very typical. And if you look, here's another example in Mexico. This is from the 100 million year Peninsular Ranges orogeny. The carbonate platform there was uplifted over the outer swell. You get a disconformity, and then it's pulled down into the trench. One of the things that you want to think about is that carbonates in tropical regimes can grow really fast. So if you just had normal subsidence, the carbonates can keep up with it, and so they would keep growing. But in the case where the passive margin enters a trench, it's actually pulled down into the trench faster than the reef-forming organisms can grow. So you get finer grained material, nicely well-bedded stuff. You get some condensed horizons. By that I mean horizons where there's virtually no sedimentation, lots of fossils and stuff like that. And then, as I said before, it's overlain by muds and marls. And then you get the flysch, the big turbidite beds coming in on top of that. Very typical. That's what you look for in a sedimentary succession that's involved in any kind of collision. Now, here's a diagram from Dick Armstrong way back in 1968. And I know that we talked about the severe orogeny a bit and how we divided it and so forth, but I want to show you Dick Armstrong's original stuff. And so here it is. Here's from his original paper. Here's a diagram showing the foreland and the hinterland and the severe orogenic belt in between, the thrust belts and so forth. This is dominantly in Nevada and in Utah. And what he did was he included everything from Jurassic to Paleocene. He just lumped it together and called it the severe 4 deep or the severe orogeny. And this is what he was talking about. And what we've tried to do is to subdivide the Western Interior Basin, the sediments of the Western Interior Basin, to reflect, in our case, the Peninsular Ranges orogeny. Here's a stratigraphic cross-section from west to east through the Western Interior Basin. Our division was built on the earlier work in the severe sector of the Western Interior Basin, mainly by Tim Lawton, and the unconformity between the lower severe and the Peninsular Ranges debris is shown by the wavy red line, which marks a major unconformity. For those that don't know, an unconformity is nothing more than a buried erosional surface. So one can use the ages of sanidine crystals from the volcanic ash layers in sedimentary strata to constrain the age of collision by using 4039 argon dating. And this diagram shows the relations of sedimentary rocks to events in the Peninsular Ranges orogeny. The muddy Newcastle is interpreted to represent the passage of the continental margin over the outer swell, whereas the Shell Creek Shale represents fine-grained material deposited on the westward slope to the trench axis. The overlowering Mowry Shale and fish scale unit in Canada is rich in both ash beds and fossils, especially fish, the bones of which are radioactive, so are easily traced in drill hole gamma logs. There's thousands and thousands of drill cores for petroleum in the Western Interior Basin. So this thing occurs basin-wide, so it's an especially good marker bed. Right where you are, at any time when you drill through this stuff. You don't even need drill core. You can just use gamma ray logs. Anyways, although all of there's lots of ash beds in the Maury and Fish scales, there were some earlier, and these are all where all the dates come from that you see on the ages that you see in little white squares in the figure. And we found that the ash beds, although they're pretty altered by seawater, we found that they're compositionally more similar to our break-off magmas rather than arc magmas. And so we interpreted them to this time period to represent the time when the slab breaks off. And by the time of the overlying frontier and Dunvegan formations, the slope of the basin floor had changed to easterly dipping, whereas before, of course, it was westerly dipping. And the basin was flooded by debris shed from the rising hinterland to the west. I'll let you see this. So one way to look at these rocks is to use detrital zircons from sandy units, and the Viking is our pre-collisional rocks, whereas the Dunvegan we interpret to be post-collisional. The Viking were deposited on the eastwardly dipping slope, and the sediments were derived from the Canadian Shield in this case, because these are Canadian samples. 1800 to 2 billion years old. And the rocks in the Dunvegan were deposited on an easterly slope and were deposited around 100 million years. And so you can see the detrital zircons, 102, 100, 101 million year peaks. These are just two ways of looking. The upper one is just a cumulative distribution, so it shows the Dunvegan's made up of really dominantly young age zircons and a few older ones, whereas the Viking are made up of old detrital zircons and sediments, and whereas there's not many really young ones. We can look at thrust belts in these collisional origins. Here's one from Nadine McQuarrie's work in South America, showing the Arequipa South American collisional terrain, and you can see the thick-skinned deformation, which involves the pink basement, and the thin-skinned deformation on top of it, and the little thrusts, the colored thrusts, which are mainly sedimentary rocks. And that's what's called thin-skinned deformation, because it doesn't include basement, whereas the thick-skinned deformation will include basement thrusts. Of course, another feature of continental collisions is slab break-off. During continental collision, the leading edge of the continental plate is subducted beneath the arc, and of course the continent is really buoyant and it doesn't want to sink, but the oceanic slab is pulling it down beneath the arc, and eventually the forces are so great that the slab necks and tears off. And this is not a great. This is an older diagram. Nick's been showing one of my more modern diagrams, but this is probably not really a good one, because this one shows a asthenosphere mantle upwelling through the tear and impinging on the upper plate. When that's probably not what happens, and the slab is probably nearly vertical at that time because of motion between the two plates is essentially stopped. And if you were upwelling mantle like this, you'd get a lot of melting just from the release and pressure. It's called adiabatic melting, and the rocks are not fundamentally basaltic that we see in post-collisional magmatism. They're granodiorites. So it's probably not correct. But the important thing is to note here is that the rift faces and the edge of the continent, a bit of it does get subducted along with the oceanic plate. And if you actually looked at the Cordilleran margin and the Appalachian Mountains and others around the world, you find that there's not a lot of rift facies rocks and not a lot of rift volcanics and sediments preserved. And so Sam Bowering and I wrote a paper, 25, 26 years ago, in which we argued that the rift facies in these big collisional origins was subducted and recycled back into the mantle. Some other things that are consequences of slab failure: you get the linear belts of high strontium yttrium magmatism, which is atypical of arcs but typical of break-off magmas. And it's been noted for a long time. They just didn't know what they were, how they were formed. They all thought they were arc magmas, but we think a better interpretation is that they form from break off of the lower subducting plate. You get a lot of deformation, thick skin deformation. Once the slab fails, the hinterland belt is rapidly exhumed. You get porphyry copper gold deposits. It's the best place to find them. And of course, the rift and transitional crust of the lower plate are subducted, as I said. Also, slab failure is marked on the passive margin of the foredeep by switchover from the orogenic flysch of the trench to molasse. So once that hinterland starts to rise, debris, of course, it can be really coarse too, is shed both east and west of the rising hinterland, and commonly with debris, commonly with pieces of sands and conglomeratic units derived from the plutons and the metamorphic rocks themselves. And they're spread both east and west, and you can date the zircons in them, and typically they're always younger than the age of collision. And then you have the depth of breakoff controls the width of the origin. So if the edge of the continent gets pulled way down 100, 200 kilometers, and then it has to rebound, it's got a really ends up with a really wide origin. Where if it doesn't get pulled down too deeply before it tears, then you get a much narrower origin. If you wanted to look and see how you might go about figuring out when an origin actually hit, you'd want to look at a place like, here's a place in the Sierra Nevada where you can see 103 million year detrital zircons in sediment associated with folded volcanics, marble units. They clearly attest to the volcanic rocks being deposited in a shallow marine environment. There was no thick crust in the Sierras at that time. And the detrital zircons, of course, provide a maximum age. So you get 3 or 4 detrital zircons, they form a peak. You say, oh yeah, that's the maximum age. It couldn't have been deposited before that, because of course that's the age of the zircons. And that 103 million age in this case is confirmed by the age of the zircons in the metamorphosed and deformed plutons, like Harriet in this case. And so the deformation postdates those, as you can see the folds in the green volcanic rocks, and yet it predates the big Sonoran Pass intrusive suite and the Ptolemy intrusive suite, which have all the geochemical signatures of post-collisional magmas, and indeed they postdate the deformation you can see here. So this is one example from the Sierra Nevada. You can find them in every origin if you look. And here's a more of the peninsular ranges of orogeny. This is just at Harrison Lake, north of Vancouver. You can see the Gambier metadacite and arc rock and all these schists are intruded by the Spuzum 96 million year pluton. So here you can bracket the deformation between 102 and 96 million years. Let's take a look at some active arc-continent collisions now. Convergence between the Philippine Sea and Eurasian plates drives the west-facing Manila Trench Luzon arc at the leading edge of the Philippine Sea plate against the oblique southeast-facing passive continental margin of China to form the island of Taiwan. Here you can see there's pretty tall mountains. A lot of people don't know this. In Taiwan, there's 14,000-foot mountains in the collisional belt of Taiwan. And the arc-continent collision is diachronous. It progresses southwesterly along the continental margin, converting it from a passive to an active margin. Every stage in the process is simultaneously active at different latitudes. South of Taiwan, the Manila Trench consumes ocean crust of the South China Sea, and the Chinese margin is unaffected. Taiwan marks the abortive subduction of the China margin eastward of the Luzon arc, causing the South China Sea slab to tear off, arc volcanism to shut down, and the accretionary prism to be engorged with sediment from the Chinese margin. You can see the fold and thrust belt and the southern part there, shown by folds and thrust teeth, and what's called intraoceanic subduction up to the initial arc-continent collision. So mountainous topography and heavy precipitation drive exhumation of metamorphic rocks in central Taiwan. North of central Taiwan, the southeast-facing Ryukyu Trench and arc marked the subduction of the Philippine Sea Plate northwestward beneath the Eurasian Plate. So rollback of the Philippine Sea slab creates a rift basin. It's the Okinawa Trough behind the Ryukyu Arc. According to John Suppy, who studied this place for years and years, the entire process from the collapse of the passive margin to the establishment of an active continental margin arc above the flip subduction zone takes around 4 million years. At a given latitude, the collision-induced mountain range rises and falls on the same timescale. Here's the topography shown in color. I've overlain the color over the island of Taiwan, and you can see the red high elevation part of the island disappears by the time you get to the north part of the island. The arc is basically gone, and the collision zone has collapsed and been eroded away. You can also see that there's very little of the arc along the edge. There's a big linear, north-south linear valley just on the east side of the red topographically high terrain, and that's what's known as the longitudinal valley, and it separates the Eurasian crust beneath it from the arc to the east. And so there's very little arc material even there to find in subsequent years. So that stuff's this is a similar process was found in or known from Papua New Guinea. Here's a map by the great Warren Hamilton, who published a book in 1979 called The Geology of Indonesia. This shows the collision between the Precambrian Australian plate, shown in white on the southern part of this diagram, with the Melanesian arc, the base of it shown in bright pink, right along the main suture there, in the middle of Papua New Guinea. Now, most people think of New Guinea as having a lot of jungles and stuff like this and weird stuff, but there's pretty tall mountains. I think there's 16,000-foot mountains in New Guinea. There's serious mountains with snow and ice and stuff on them, that's the fold and thrust belt nowadays. The real hinterland belt has largely eroded. It's where it's shown in this map where the Melanesian arc terrain was, and the fold and thrust belt high altitude zone is now just to the south of that, and that contains the 3.6 to 2.8 million year Erzberg-Grasberg plutons, post-collisional slab break-off plutons, and the Star Mountains octeti. My friend John Doucette worked on octeti years ago for his PhD dissertation, and he's now over in Thailand with his girlfriend. But anyways, the Melanesian arc terrain was accreted to the northern margin of the Australian Craton at about 12 million years ago, and the uplift and erosion has lasted for less than 12 million years now. And here's a diagram from southwest to northeast, cross sections through the mountain range in the top to show the actual topography. And you can see from the lower one, which shows total denudation, there's 25 kilometers of debris in the metamorphic belt eroded already. It's gone. It's got a lot of high rainfall and strong exhumation in that. So the arc is basically wiped out. It's gone except for the arc basement of some ophiolitic rocks at the base and so forth. So it's pretty hard again. It will be pretty hard again to find a lot of arc rocks. And the thrust belt is still preserved. It's up to like nearly 5,000 meters high. Those are some of the pictures that we showed. And that's where the post-collisional plutons are now. So this is the Taiwan collisioning cross-section. Shows you the central range duplex there. The area that's being exhumed and eroded, and shows you it's flipped around actually, but that's okay. The lower diagram is a scaled model done by a French guy, and shows basically the same thing. He scaled it and produced the same kinds of structures. Another good place to see the hinterland belt, the exhumed hinterland belt, is in British Columbia and the Yukon Territory, where Dick Armstrong again demonstrated a strongly metamorphosed and exhumed belt full of early Cenozoic, tertiary in the old terminology, plutons that are clearly slab break-off plutons based on their composition and their timing as well. And they're placed into this exhumed terrain. A lot of people think this is an arc, but it's nothing like an arc. It's got really 25 kilometers of uplift and all these plutons. And, these rocks are shown on the tectonic map of Canada and Wheeler's map of the Cordillera as metamorphic rocks. They're not even subdivided. They're at such high grade. Anyways, the pre-collisional volcanic rocks are always typically best interpreted as an arc. They're built on continental crust in many cases and are interbedded with shallow marine sediments, so there's no thick crust. And we talked about this in the previous talk as well. Post-collisional plutons are placed at 4 to 10 kilobars, and so up to 30 kilometers, say, in depth, and they were rapidly exhumed and eroded. And there's lots of detrital zircons in basins on either side of the hinterland that are derived from these plutons and clearly demonstrate that the basins are younger than the hinterland, the collisional zone. A good place to see what collision you might get a cross section through it is in the San Emigdio Mountains at the southern end of the San Andreas, which were obliquely uplifted by the Laramide Deformation in the Mojave. Notice north is to the upper left of this diagram. And there you have 135 to 100 million year plutonic rocks, dominantly gneissic, but not all strongly foliated, but generally gneissic. And they have paleo pressures of up to 10, 12 kilobars. So they're deep-seated rocks. They sit atop the San Emigdio schist, which is a schist much like the Pelona Orocopia, the Swakane gneiss and schist. And this one is got a paleo temperature of 700 at the top. It's hot side up, 550 at the base in centigrade temperatures. And so it sits right beneath all the arc rocks and above metasedimentary rocks of what can only be interpreted as part of the North American craton. And they're very much like, in terms of their debris, like rocks you'd find in Death Valley or in the main passive margin to western North America. They have a clear tripartite detrital zircon signature, as you can see in the left diagram. And they're all now intruded by a post-collisional pluton, which is about 90 million years, so about as young as 10 million years afterwards. But the area was being exhumed rapidly because by 92 million years, the Lebec granodiorite was emplaced at 3 kilobars. So you went from 10, 12 kilobars to 3 in about 10 million years. So the exhumation was pretty severe. And note the San Emigdio schist in the lower part of this figure has 99 and 100 million year detrital zircons, so it can't be any older than that. So this is a good cross section. Now the interesting thing is there's nowhere to the west of this where you can get these sediments that sit beneath the Sierra Nevada. They are part of North America, and the Sierra Nevada is sitting up on top of it. And so that clearly documents westerly subduction, where the Sierra Nevada is sitting on top now of North America, and this has preserved this little area. This is from the excellent work by Alan Chapman and the now deceased Jason Salibi. Jason was a graduate student when I was an undergraduate at Santa Barbara and demonstrated me. I think it was an igneous class. But anyways, it's a great map, and they have a slightly different interpretation. You can dig up Alan Chapman's work if you like. And I think it's some schist caught in between these things. Well, to me, it shows that the Sierra Nevada arc sits on top of the North American craton with a little bit of this schist hot side up between the two. This was a hot arc. Now that brings us to back to this triad, and I used to call it the Holy Trinity because it's kind of almost a dogma or paradigm of Cordilleran geology, that you have the Sierran Arc with thrusts all to the east side of it, and then you have the Great Valley four-arc sequence, which is debris out in front of the arc, and then that's sitting on top of the Franciscan accretionary prism, the subduction complex. But the problem with the Great Valley sequence being a four-arc basin is that much of it postdates the age of the collision. It's younger than 100 million years. And this is a diagram, I think Nick showed this diagram, but it's from our one of our slant papers in Canadian Journal of Earth Sciences. And if you go through this, down at the bottom, you see the Valle group, and it's got all of these in this purple have 99 to 83 million year debris in them. And you can go all the way up and down the coast, the Valle group, the Great Valley, the Ochoco Basin in Oregon, the Cascade River Schist in Washington, and lower Nanaimo, the Queen Charlotte group, and the McHugh complex of turbidites and or other debris in Alaska. And all of these contain detrital zircons younger than the age of the collision, so they can't be forearcs. They're material that was deposited to the west of the collision belt, just like the rocks were deposited to the north of the Papua New Guinea Australian collision. And you can also see the same thing along in the coast plutonic belt in British Columbia and the Yukon. There you have the Chugach accretionary prism rocks, and they're 60 to 70 million years based on younger than 60 to 70 million years based on detrital zircons. And of course, the paleomag says that they need to come back farther south and shown in the colored map to the south. And so the hinterland belt to the Laramide is shown on the right-hand diagram, where before it was in colors. You can scroll back if you like and see the colored version of it, filled with the post-collisional plutons. So Chugach is not accretionary prism rocks. They postdate the collision quite clearly. Similarly, you could look at the Jurassic Wrangellia talkeetna Naknek Basin in southern Alaska. And this is from the work of Harriet and Wardis. Some cool stuff up there that they've been working on, and I hope Nick gets out to see this stuff this summer, because he'll probably get so excited he'll need to go to a private room. But anyways, you can see the big thrust reverse fault, actually, a high angle reverse fault in the upper left-hand diagram, bringing up the hinterland belt and shedding debris off to the east. I think that these big reverse faults, which are pretty common along the edge of hinterland belts, may mark the edge of the subducted lower plate as it rises and lifts the rocks above it. Anyways, this is on the two diagrams, or three diagrams to the right, show some big outsized 2-3 meter clasts. And I threw these in for Nick because he seems to like large clasts. These are dioritic clasts in the conglomerates there. Pretty proximal deposits being shed off this uprising. Similar sort of deal at Harrison Lake, just north of Vancouver. There's your 102 million year dacite again. Big, giant reverse faults at Harrison Lake, separating rocks at 10 kilometers burial from 35 kilometers. So that fault has 15 kilometers of uplift on its eastern side, vertical displacement on its eastern side. And again, just like the stuff we saw in Alaska, this is also related to the Peninsula Ranges orogeny, which is why I have figures of it. And this one is from Mexico, in Baja, shows the same thing to the west again. Here's the main Martyr thrust and the Rosarita thrust. They're both big reverse faults with many, many kilometers, 10 or more kilometers of reverse uplift on the eastern hinterland side. Notice all these dated plutons at 5, 6, 7 kilobars, so 20 to 30 kilometers in depth. And again, that's typical. So one of the things that you'd like to know is, how does subduction start? A lot of people ask questions about that. They say, well, does subduction flip, or what happens? And so I wanted to talk a little bit about that and see if we can answer some questions, or maybe show how little we know. One place to look for that might be the Indian Ocean, where India just was partially subducted beneath the Eurasian continent. And so you'd think that there would be a good place to see subduction flip. But that's not happened. Despite the Indian Ocean floor being folded during the Miocene, big folds, and there's over 20 kilometers of sediment in the Bengal fan coming out of the rivers there. And So, this Bengal fan thing is pretty much like, or might be a good analog for the Belt Purcell, which is just 20, 25 kilometers thick. Of course, during the Mesoproterozoic, you had no plants or anything, so the sediments might be a little bit different, but they're dominantly clastic sediments there, and they're very, very thick. So that's one possible model. Another model for the Belt Purcell might be a Caspian Sea-like basin, maybe Black Sea, I don't know. But I think Paul Hoffman liked the Caspian Sea. But at any rate, there's no evidence that you've got any kind of subduction forming here. And it's a great place because the Indian Sea Plate is moving northward, but yet it seems really strong. Another place where you'd think might be a good place is the Arc-Arc collision in the Moluccan Sea. The Moluccan Sea is the actual collision zone, now dominantly below sea level. And yet on either side of the collision zone, you have in the east the Philippine Trench there, and you have this North Sulawesi Trench, which goes up into this trench in by the Philippines. It seems to be covered there in that central part or unresolved on this map by Warren Hamilton. But anyways, there's no subduction flip. Subduction's the same direction as those on the arcs that collided. I do know one way you can start subduction in an ocean basin, and that's by infecting them. So here's a case where the Lesser Antilles, along with the Caribbean Oceanic Plateau, has migrated from the Pacific Ocean through the gap between North and South America. And Kevin Burke called it the Great Arc of the Caribbean. And he was a student of the Caribbean, actually, and many things, but he was especially interested in the Caribbean, maybe because it had tropical islands and stuff. But anyways, he recognized that it pumped through, and of course it left debris all over North and South America, Colombia and Ecuador, and then has a big transpressor regime across the northern part of Venezuela, which is interesting. Big faults and lots of folds and stuff, and it's basically a collision, a very, very transpressional collision between the arc and South America. I've shown three different models from top to bottom here. They're not really that different, but I had it once in a paper that I wrote, and so I threw it in here. And if you want to figure it out, you can try to see the differences between the three. They're not great. You have the Caribbean Oceanic Plateau formed at the Galapagos hotspot, and it's got arcs on one side or the other or both, and of course in all three models they end up with arcs on either side. And it moves in through the gap between North and South America to form the Antillean arc. So it's infecting the Atlantic Ocean with an arc. Now it's pretty interesting because a lot of people think you could only form new subduction zones at mid-oceanic ridges because the ophiolites that you find in collision zones have a metamorphic soul, high temperature metamorphic soul, and suggesting that the area was quite hot. But you haven't formed any at the mid-oceanic ridge yet. So I don't know if that's true or not, but that's probably one place where you could start them. I think that probably in marginal basins, where marginal basins also have a ridge system in developed marginal basins, of course, behind the arc, and they close by subduction. So you could possibly form new subduction zones in mid-oceanic ridges of marginal basins. Those would be thin, much thinner, than true oceanic lithosphere. Anyways, another place to see the Atlantic Ocean being infected is, of course, between South America and Antarctica, where the Scotia Arc has burst its way through and almost like an alien finger into the Atlantic plate, and or still South American plate, but into the Atlantic Ocean. And it also is infecting the Atlantic Ocean. So that's one way. What's going to happen in the Atlantic with these two little arcs? Who knows? Time will tell. One of the things that I worked on years ago with Eldridge Moores, we both didn't really think that Cordilleran origins, which are like long-lived eastward subducting origins, say between North America and South America, really existed. Although today subduction is beneath both continents. But we didn't think that was always the case in the past. And so we started a project, and unfortunately Eldridge died before we were able to significantly complete this project. But we looked at the Laramide Deformation, the last major collision of Western North America and South America. We found that it occurred along the whole length of North America, and that all the four deeps of that age in North America were, along with the thrusts, verged eastward, and that there wasn't any magmatic arc of that age on North America. And so they all suggested to us that it was partially selected to the west beneath the Cordilleran Ribbon Continent. And we looked at South America, of course, and it was the first paper I published with Joe Whalen was on the geology of South America and the Peruvian arc of Peru. Anyways, you can see here the north part in Colombia, this again is tipped up on its side because it's long and thin. And the northern part through Colombia and Ecuador is the collision of the great arc of the Caribbean during the Cretaceous. And then there are various accretionary stuff all along, all the way down to Tierra del Fuego, and probably continuing to the Antarctic Peninsula. But these are, you can see the batholiths in red, mostly post-collisional batholiths again. And so we recognized that, wow, there's a collisional event that goes all the way from Alaska to Tierra del Fuego, maybe beyond. It's just like these giant orogenic belts, the Alpine Himalayan belt, which goes all through Europe, through Turkey and Iran, through Pakistan and Afghanistan, down down into Southeast Asia. Another one of these big, giant, long, they're great circle origins actually, and form on great circles on the surface of the Earth. And also the peninsular ranges. Orogeny goes from Alaska to at least Peru. We've been able to find. Maybe it goes further. And so we recognized this, and we wondered, wow, how is that even possible? How do you get repeated westerly subduction along the western margin of North America, and why do you have all this downwelling? What's the deal with that? And so we recognized that this was up and down the whole margin, and we also realized that it was a zone of major downwelling. Huge amounts of oceanic lithosphere were subducted beneath whatever terrain lay to the west of North America. So how do you get so much subduction? How do you have so much downwelling on an Earth that's not expanding? There must be complementary upwelling zones somewhere. So we started poking around, and of course we realized pretty quickly that we needed to talk about the work of Kevin Burke and Trond Torsvik, who looked at hotspots. And hotspots are roughly cylindrical zones arise from the mantle, form volcanoes in the Earth's crust. They're not fixed, as people used to think. They'll migrate a bit, not much, but they tend to form two clusters. One around the southwestern Pacific, and another around Africa. Now, if you look at the ones in the Pacific, of course, here you can see the Hawaiian hotspot track, and it goes and then takes the big bend at about 50 million years, maybe 47, but somewhere right in there. Interestingly, the same age as the collision of Silesia, and roughly about the same age that you have all the final thrusting of the Laramide associated with the northward migration of the Tintina Rocky Mountain Trench. So there may have been a major plate reorganization at that time. Of course, some people used to think that Hawaiian hotspot was fixed, but now we know that it's probably moved from the north to the south, and would account for about 20 degrees of the Great Bend, with 60-degree bend, so it would knock it down to about a 40-degree bend. But anyways, you can see all of the seamounts, all of the volcanoes on the floor of the southwestern Pacific Oceans, huge numbers of them. Here they are. Here's a better view of those southern ones. You got big plateaus, tons of seamount tracks as the ocean plates moved over the hot spots. It's a pretty cool thing, actually. And back about 1963, the great Canadian geologist J. Tuzo Wilson first recognized that volcanoes on the seafloor were hotspots. and called them that. And he also argued that the plates had to be moving over them because these hotspots left big trails. You can see the trails to the west of western South America there on both sides of the ridge. Of course, things move opposite away from the ridges, and they're symmetrical. And there's another one on the other side of between South America and Africa, that you can see. So that was a big thing back in the early '60s, and one of of course, J. Tuzo also pointed out and understood what the transform faults on the mid-oceanic ridges were. They're places where plates can slide across each other without consuming any material. So naturally, we turned to the work of Burke and Torsvik, and they showed that Africa has been sitting in the same place for at least 200 million years. Some people say a billion, but they say 200, 250 million years. You can see on the left the movement of the of Africa, shown in white. And beneath Africa and Pangaea, what's known as Pangaea A, it has two different models, Pangaea A and Pangaea B. But this is Pangaea A model, and there you had a low velocity in the lowermost mantle beneath Africa and Laurentia. It's dominantly beneath Africa. And in that region, when you restore the current hotspots in large igneous provinces back to 200 million years, they all cluster around either the low velocity zone, which you find in the southwest Pacific Ocean, and beneath Africa. So, Africa, so like it showed, Africa hasn't really moved. So that's how far North America and South America have moved as far away from Africa as the width of the Atlantic Ocean. Africa has hardly moved, maybe 400 or 500 kilometers, maybe moved the other way, I don't know, but not much. So you can see that North and South America have moved a lot westward, and that's why when you look at magmas coming up beneath collisions, they commonly are farther east in the collision zone than the original tear, because North America is actually moving across the tears, just as the oceanic plates move across hotspots. So at any rate, they found that the hotspots, the zones of upwelling, mantle upwelling, occur around these low velocity zones at the base of the mantle. These zones sit just above the core and are low velocity zones. Recent work by Talavera Souza, published I think last January or February, showed that the low velocity zones, shown in red here, plumes came up from alongside of them, were subducting slabs, and the slab graveyard where all the slabs were ponding at the core mantle boundary were zones of cooling, and that they were dominated by much smaller grains. It changes the velocity of the waves that they measure, whether it has small grains or large grains, and and also in the temperature and composition. So we don't really know truly what these things are, but they're big zones, they're consistent, they're easily seen, and people have been working to try to understand what they are. But they're clearly, whatever they are, zones of significant mantle upwelling. And they are the counterpart on a non-expanding Earth to the subducting slabs, or the downwelling. Here you can see a westerly dipping slab into the slab graveyard. So this seemed to be something that fit our ideas pretty well. One of the things that we looked at, here's an equatorial view showing the geoid highs and lows. These areas of low velocity are named Jason and Tuzo. Jason is the one in the Southwest Pacific. Tuzo is the one over Africa, or under Africa, sorry. And you can see the slab graveyards with sinking mantle occurs between these on both parts of this equatorial vision, above and below of the outer core. This is a pretty cool idea. I like this, and goes a long way, I think, to explaining why we have such long-lived westward subduction. Here's a figure that was published by Eldridge Moores. I think it was in Science maybe Nature, but Science, I think, in 1970. And it was a diagram which I've colored and shows the Laramide system separating the Panthalassic oceanic realm from the Proto-Pacific at that time, and showing, following collision with North and South America, how it passed the arcs, the arc itself passed through the gaps between the two to infect the Atlantic Ocean with subduction zones and arcs, that are there in the Caribbean, the Lesser Antilles, and the Scotian arcs today. So it appears to us that the ribbon continent represents material assembled over a long-lived zone of mantle downwelling. And how composite was it? We don't really know. But it's a major first-order problem in the Cordillera as to how these various terrains were assembled. Things broke off from North America again, and perhaps during the upwelling of slab failure magmas, and opened up, went out and collided with a block off to the west, and then came back into North America. Wrangell appears to have done that, collided during the Jurassic, and then collided again during the Cretaceous. Yeah, it's a pretty complex thing, but we think it goes greater than just understanding the Cordillera. We think you need to work through this stuff to understand whole convection and how the kinematics of the mantle work, because it no longer can be viewed as just a continuous, well-mixed mantle. It's clearly got zones that are filled with slabs and zones that have peridotite that were charged with fluids and whatnot. So I'll leave it with that.